Let me begin this talk with a big picture and a big question. The big picture is on astronomy on a large scale, cosmology. So we are talking about galaxies, galaxy clusters, we're talking about the universe. And the question is whether the physics of the microscopic world, that is quantum physics, plays any role in the physics of the absolute microscopic, the universe, galaxies, stars, and so on and so forth. And I would like to explain in this talk that there are in fact some connections, but also that there are connections not only in a direct way, but in an analogous way, that features that occur in cosmology you can also find on Earth, on scales that are familiar to you, and you can test them in experiments conducted in ordinary laboratories, for example, in optics laboratories, or even in fluid mechanical laboratories. So that's what I want to talk about in this talk. And this work is inspired by two great scientists who unfortunately recently passed away. One is Jakob Bekenstein, who discovered that black holes have thermodynamic properties. They have an entropy. They behave like a thermodynamic quantity. And the other one is Stephen Hawking, who also left his wheelchair this year, and who discovered that black holes are radiating. And they're not entirely black, but they're sending out radiations. These two features are connected with each other. And let me introduce this in a simplified picture, and let me explain first to you what this picture means. So this is an illustration of a black hole. In the center you see the singularity of the black hole. The black hole is a collapsed star where gravity is so strong that it has collapsed essentially to a single point. The singularity is surrounded by an event horizon. The event horizon is the place where nothing can escape anymore. Not even light can escape from the black hole, hence the name black hole. And what Jakob Bekenstein has discovered, that this event horizon behaves as if it were an object of thermodynamics. So its area gives you, it's proportional to its entropy, for example. And what Hawking discovered is that moreover, because it is of a thermodynamic nature, it sends out radiation that appears like thermal radiation with a temperature. And what happens there is this, that the quantum mechanical vacuum is a physical state of where nothing happens, and everything is zero, so to say. And this quantum mechanical vacuum still interacts with the event horizon and is able to produce pairs of particles. For example, photons, light particles. One of those particles escapes and becomes visible to an observer, and the other particle falls into the singularity of the black hole. And if one then looks at the particles that escape, they really behave like thermal blackbody radiation. And what is remarkable about this radiation becomes apparent if you look at Hawking's formula for it. This is the formula for the temperature, and that this is a remarkable result you see from the constants of nature that occur in this formula. They are shown in this diagram down there. So you have h bar, that is Planck's constant, that stands for quantum physics. You have big G, Newton's constants, and c, the speed of light, and both belong to the field of general and special relativity, that is physics of gravity. And you have Boltzmann's constant, and that belongs to the area of thermodynamics. So this physical effect that event horizons radiate, they produce particles, seems to create a connection between two areas of physics that are normally not connected, and that is quantum physics, gravity, that is general relativity, and thermodynamics. That is what makes this effect interesting. So if you then look for theories that try to connect this, for example, quantum theories of gravity, then the first thing that is done is to reproduce this feature, and if the theory has that feature, then you would see this as a confirmation that it might be in fact correct. And that's the good news of this formula. The bad news is if you put in numbers in all of these constants, and you find that the temperatures that astrophysical black holes have are very low indeed. They are much lower than the temperature of the cosmic microwave background, or even the fluctuations of the microwave background. So in order to see this effect in astrophysics, there's no real chance. Even if you would have a black hole that is completely quiet, there's nothing falling into it, the chances of observing it would be very low indeed. However, you can see something similar in analogs of it. And let me explain to you what this analog is. And first, the person who pioneered this field is William Unruh, who pointed out that with the help of fluid mechanics, in particular quantum fluids, one can simulate black holes. And let me explain how this goes. And it is based on a beautifully simple picture. This is the picture. This is a black hole. It goes like this. So imagine you have a river. This river is getting faster and faster and faster until it reaches a waterfall. Singularity falls where the water falls down. And this river is populated by fish. The fish, however, cannot swim arbitrarily fast. They have a finite speed, c. The water can become faster than the speed of the fish. So there is one point where the water flows faster than the fish can swim, and on one side, and on the other side, the fish can swim faster than the water. And so on this side, on one side, the fish can escape, they can swim upstream. On the other side, they cannot do this anymore, and however strongly they try, they will drift backwards and be crashed at singularity falls. This is what a black hole does. The point of transition, so where the speed of the water is equal to the speed of the fish, that is the event horizon. So what a black hole is, it's like space crashing into the singularity like a river, and then everything else is swept away by it, in particular light, and the horizon is the place where the flow of space and time reaches the speed of light. That's what a black hole is. And so now you can understand black holes by analogy, but it is not just a crude analogy of what a black hole is. It is actually a mathematical identity. So one can show, and I use these equations to illustrate that the equations that govern not fish in the water, but waves in the water. This could be sound waves. This could be the waves on the surface of the water, anything that is described in form of a wave. This satisfies a propagation law that is exactly the same as the propagation laws of waves in a space-time geometry. So one can therefore mathematically prove that these pictures of waves in moving fluids and waves in space-time geometries that correspond to black holes are identical. So what would Hawking radiation then mean is it would be the spontaneous creation of particles in such fluids, or in the language of fish. So fish would be spontaneously created on one side of the horizon, and then there's an anti-fish on the other side of the horizon, and that of course is quite a fisherman's tale, so it probably has never been observed in practice. And that already indicates that to do experiments like this is not entirely straightforward. And so we are doing experiments that test the theory of particle production at horizons, and we're doing it with light. That causes another problem. So if you want to do experiments of this kind with light, that means you have to replace these fish by light waves. Then you need to have a medium, a material that moves as fast as the speed of light in the material. That's not forbidden because materials typically reduce the speed of light, but not very much. So in water, the speed of light is reduced by a factor of roughly 1.3, and so light is still very, very fast indeed. So how can you do this? So how can you make materials move essentially at the speed of light? So that sounds quite impossible, but I found a trick to do that, and the trick is the following. So imagine we have a fiber like an optical communication fiber. Now the laser pointer has died, and let me simply describe it with my hands. And so imagine you have a waveguide and a light pulse inside of this waveguide. Now what the light pulse does is it changes the refractive index, it changes the speed of light slightly. As if you would have an additional piece of material where the light pulse sits. So, and then you can send probe light, for example, after this additional piece of material, and this probe light would then experience it would get slowed down by it, and it may not be able to overtake the light pulse. And so there you have an event horizon. Now, this horizon, or this perturbation of the refractive index, it is created by light, and therefore it naturally moves at the speed of light in the material. So, sorry, I need to drink. So therefore, to make a material, or to create a situation where something appears to move with the speed of light is very simple. All you need to do is to send light inside of, in this case, a fiber. And then the perturbation of the refractive index that the light itself creates appears like a moving medium, and you can do physics of the event horizon with it. However, if you want to get into a regime where you have a chance to observe subtle features like the spontaneous creation of light particles at the horizon, you need it turns out you need very, very short pulses, and you need sophisticated fibers. So you need lasers that are able to create light pulses that oscillate just at a few cycles of light. These are the Ferraris of lasers, and they are as expensive as a Ferrari. And you need fibers that are sophisticated, that carry structures inside in order to control the speed of light in a way that is required. And when we started this research, we didn't have the money for the Ferrari. We only had money for something like this. And nevertheless, we did already, we could observe an effect that is related to the physics of the event horizon with our experiment. And this was an effect where light that probes the horizon gets shifted in its frequency. So it tries to overtake the pulse. It cannot do this anymore. And it gets a bit stuck. So the wavelengths get shorter, and that appears as a change in the wavelength in the spectrum, and that's what we had observed. And several years later, I moved to the Weizmann Institute, and there we started these experiments again from scratch. And initially it looked like this. was done with 2 PhD students, and then things began to move. This is how it looks now. And this is our setup, and relatively recently we got the first of our results. And let me explain what we have observed in this experiment. What we did was a modification of the scenario that I told you at the beginning. The scenario that was at the beginning that was this, that the quantum vacuum is creating spontaneously particles at the event horizon. One particle escapes and the other one falls into the singularity. What we can make in the laboratory is, for now, is not the spontaneous creation of particles, but the stimulated creation of particles. So we seed it with a light beam, and that makes the effect stronger. So we create then more particles that are escaping, and we create particles that are falling in this picture towards the singularity of the black holes. This is the scenario of our setup. And let me try to explain what is going on. So what we do is essentially to recreate the situation in this cartoon picture. So we have a light pulse, and then we have light that probes this pulse. And that in the experiment begins with light pulses that are about 8 femtoseconds long. They are split into 2 parts. So one part becomes our pulse in the piece of fiber that does all the action, and the other part becomes the light with which we probe the physics of the event horizon. And we generate this by sending the probe light into another long piece of fiber, and in this piece of fiber it becomes changed in its frequency, and then we combine everything together in a very short piece of fiber, and then we look what happens. Now, what happens is this. So depending on the frequency of light, so depending on whether the light is such that it is, or depending on the speed of the probe light, whether it's faster or slower than the pulse, you have 2 different scenarios. So if the probe light is faster than the pulse and is trying to overtake it, so it's running towards it, then it's like in this picture as if the light waves would run up an obstacle, their wavelengths become shorter, and then they reach a point that they cannot pass anymore, and then they fall back. And so you create an effect that corresponds to the blue shifting of light. The wavelengths become shorter. On the other hand, if you have waves that are slower than the pulse, then those waves do exactly the opposite. So they would fall down from the obstacle, so they become longer in their wavelengths and redshifted. And that's what we see in our detection apparatus. So we have now, depending on the speed of the probe light, and the speed of the probe light depends on the frequency that we choose. And you have 2 different scenarios. In one case, we get shifting towards shorter wavelength, that is blue shifting, or shifting towards longer wavelength, that's red shifting. So we reproduce what we had seen in the earlier experiments, and we use this as a mechanism that tells us that we do have an event horizon. We begin to see physics of the event horizon. The new feature of our experiment is what is shown here under UV detection. So this UV detector measures the part of the light that is on the wrong side of the event horizon. So we see the light that in the cartoon picture corresponds to the light that escapes towards the observer. This is the light that we seed the horizon with, that becomes blue or red shifted, and the light that falls towards the singularity. That, in our case, is light in the UV part of the spectrum, and these are our latest measurements that you see over there. And from those measurements, we can extract a feature that is due to the pump light that we send in, and that is consistent with the prediction where and which part of the spectrum we would expect to have this light generated. So that gives us a confidence that what we see in the experiment is in fact this effect of stimulated Hawking radiation. So that's the work with lighted fibers, where we use essentially a black hole that is made, or event horizons that are made of light, and we observe light at the horizon. And this work was done primarily by two PhD students, Jonathan Drori and Yuval Rosenberg, and with great help from theory postdoc David Bermudez, who is a faculty member at Institute of Advanced Studies in Mexico City, and by my colleague from the Weizmann Institute, Jaron Silverberg, who contributed with very good ideas to this work. And this is one subject I wanted to talk about. There is another on quantum effects in cosmology, which is closely related to the physics of the event horizon. It's also an effect that has its origin with William Unruh, and it's called the Unruh effect. This work was done together with three gentlemen from the Institut Langevin in Paris, in particular Matthias Fink, and another PhD student, a theory PhD student from the Weizmann Institute, Itai Grignasti. Now, it goes like this. So imagine you are out in space. And how does space look like? Like this. So you see nothing. Now imagine you're moving through space. You're moving at uniform velocity through space. This picture would not change, because according to the laws of relativity, all systems moving relative to each other with uniform velocities are identical or equivalent. Physics would be the same, so you wouldn't see anything. However, now imagine you are accelerated. So you press the accelerator of a rocket engine, and you're racing through space at uniform acceleration. What you would see would be this. So particles would be rushing towards you. So empty space is no longer empty to an accelerated observer. Also, this is an effect that appears like thermal radiation. It's described by an effective temperature. This temperature now depends on the acceleration, and it depends on the speed of light and on Planck's constant. So like in the case of Hawking radiation of black hole, it combines various areas of physics, combines the physics of general relativity here in terms of acceleration, quantum mechanics, and thermodynamics. And similarly to Hawking radiation, if you put in numbers, you realize how difficult it is to observe this effect. And here's an illustration. So if you want, with this temperature, if you want to reach room temperature, you would need an acceleration in the order of 10 to the 21 g. So 10 to the 21, the acceleration on the surface of the Earth. It would crash everything. And so that's quite a challenge to get accelerations like this. And this is not, as it turns out, it's not the only challenge you would need to face in doing experiments of this kind, and that's something I would like to explain. So let me first explain this effect. And the way I will try to explain this is by drawing a diagram in space and time called a spacetime diagram. The horizontal axis represents space. The vertical axis represents time. Essentially, a spacetime diagram is is a video. And what is shown in this diagram is the trajectory of an accelerated observer. What you see there is that the observer comes in from the distance with minus the speed of light, then it gets reduced in speed until for a fleeting moment the observer stands still, and then it becomes accelerated again and leaves with the speed of light. And so that's as it turns out, that's the exact trajectory of an accelerated observer at uniform acceleration. That's one part of the story. The other part of the story is that this accelerated observer, of course, moves at very large velocities. We know from relativity that the speed of clocks becomes velocity dependent. So if something moves very fast, then time ticks slowly. If something moves slower, its time ticks faster, and vice versa. So the ticks of times are here indicated by the different colors. So showing that when the accelerated observer is at a fast velocity, its time runs relatively slowly, and close to the turning point, its time ticks at the normal value, so to say. Now, the Ono effect appears. So if you have one accelerated observer, then this accelerated observer would measure particles, for example, photons, in a detector. And in its most dramatic form, it actually appears if you have two accelerated observers. So imagine that in addition to the one observer I just talked about, you have its exact mirror image. We have another observer that also comes from the distance, gets closer, and then leaves towards the distance as well, in exactly the mirror image fashion of the first accelerated observer. Then the second observer would also see, instead of the quantum vacuum, it would see fluctuations. So it would measure thermal radiation. But if these two observers would then be able to observe what they have seen afterwards, what they have seen per spectrum, and compare the notes, they would find, to their surprise, that whenever one observer has measured one photon, so has the other. And so despite the fact that these two observers see a phenomenon that appears to each of them completely random, these phenomena are in fact not random at all. They are closely correlated with each other. Why is this so? And this is so because the noise of the quantum vacuum, fluctuations of the quantum vacuum, and other forms of wave noise as well, this noise appears at a given moment in time as completely random, but it is no longer random if you visualize this as a space-time diagram, as is shown in this picture. So as before, so the horizontal axis is space, the vertical axis is time, and what this picture shows are random waves propagating now in space and time. And you see that so at a given moment in time, everything is completely random, but in space-time, you can clearly see structures. You can see causal cones appearing, and so in space-time, wave noise is organized. And this organization then leads to correlations across space and time. That's one side of the story. The other side of the story is this. Each one of the two accelerated observers, and when looking into a particular frequency of the light that this observer is susceptible to, sees this frequency corresponds to a wave that is monochromatic, in the sense that it ticks always with the speed of the clock of the accelerating observer. But you know that the speed of a clock depends on velocity. So if the accelerated observer is in a region where it's very fast, then the clock speed is slow. Then close to the turning point of the motion, the clock speed becomes normal, and then it's getting slow again. And this picture gives you the wave that corresponds to this clock speed. So initially it has a very long wavelength, and the wavelength gets shortened, and then when the accelerated observer moves out, then it also crosses the crests and lobes of these waves less and less frequently, such that they correspond also to the slowly ticking clock of the observer that moves in with a very large velocity. And the same is true to the other side. So you have these two types of waves that correspond to the two types of detectors and that take into account this relativistic time dilatation effect. Now the UNO effect is the result of the conflict between these two pictures. So that is correlations of noise seen by waves or analyzed through waves that are that cut space-time into two parts and that are following the features of the accelerated observers that are slowly varying and then getting faster and faster close to the horizon of the accelerated observer. So that gives you that gives you correlations, and these correlations, they appear as in form of particles and form of additional noise that the accelerated observers detect. Now, that is a theoretical picture of the physics of the event horizon, or the physics of the horizon as seen by accelerated observers. And what we have done is to recreate this physics in the laboratory using water waves. And why we're doing this is because let me explain the main idea. So instead of using the fluctuations of empty space, the quantum vacuum, what we're using is fluctuations of a water surface. So imagine you have a tank with water and then small ripples on the water surface, and this is noise, this is wave noise. And imagine you observe the water surface through a trajectory that simulates the trajectory of an accelerated observer. You could do this, for example, with a mirror and a laser beam. And the laser beam then follows exactly these trajectories of accelerated observers, with the difference that instead of the speed of light, you're using the speed of the water waves. Now, water waves are significantly smaller than in its speed than the speed of light. So that already is an effect that enhances the temperature of the UNO effect. The other thing is that if you don't work with vacuum fluctuations, but with classical fluctuations and ripples of a water surface, then you can make those bigger than the vacuum fluctuations, and that also enhances the effective temperature, and you can get into a regime that becomes experimentally observable. In our experiment, we did even a further simplification. So what we had was not a random ripples on a water tank. So we had a water bath put on a shaker, and what this shaker does, it creates a standing wave pattern on top of the water bath by a Faraday instability. And then we simply took a video of this wave pattern and analyzed the video afterwards. So we analyzed it such that we put in the trajectory of an accelerated observer on it and then ask what happens with it. Now, if you have a finite water tank, that means you also have boundaries in your system. And these boundaries, turns out, lead to interesting effects. They act like mirrors. So if you have, in the original picture about the two observers, so one on the right side and the other one on the left side, and the two observers would see correlated particles or correlated waves. If you place a mirror between the two, what happens is then you can work just with one of those accelerated detectors, because the mirror then projects the fluctuations from the other side onto on the trajectory itself. So instead of getting correlations between the two accelerated observers, these correlations appear in the trajectory of one observer alone. And that's one advantage, or this is one of the features of the effect of boundaries. And the second one is that because of this relativistic dilatation effect, in order to get reliable data on the Unruh effect, you need to sample for a long time. And that means also for a long distance. And if you have two boundaries, you can choose mirror images of the accelerated trajectories, and that cuts you the distance in space, so you don't need a very large water tank anymore. You can work with a small tank, just using the fact that you can mirror image the trajectory of the accelerated observer at each piece. That's what we have done, and we needed also a third trick, and in order to cut the observation time that I'm not going to explain because it's quite mathematical. And now, what we have observed is pictures like this. So these eye diagrams, they show the correlations. So if you analyze your data of the change in the water surface, then you see that for one component you get large fluctuations, and for the other components you get small fluctuations. That's in fact called squeezing. And that depends on frequency, and we have these diagrams show you this squeezing effect for three characteristic frequencies, where we compare it then with the theory. And for two of those values, we could in fact plot this then over a Planck spectrum, and we get these 2 points. That sorry, it's still a very preliminary results. And but these are the first 2 points ever close to a Planck spectrum of an Unruh effect observed so far. Right. So this is what I wanted to tell you in this lecture. The take-home message are these pictures. So one picture is about the physics of the event horizon of the black hole, is that you can mimic black holes in the laboratory by moving fluids. There you can replace the physics of space involved by the physics of a fluid. So as if space is simply around the black hole is a river streaming towards a singularity, and then when waves move or when this river exceeds the velocity of the waves inside of the river, you do have an event horizon. That's the first take-home message of this talk. The second one is related to the physics of accelerated observers. And it's illustrated by these 2 pictures. So if you have accelerated observers, then you get a conflict between, on one hand, that each of the accelerated observers has only access to a certain part of space-time. Space-time is cut into 2 parts. You have an horizon in between, whereas the noise, be it quantum fluctuations, vacuum noise, or classical noise, fills the entire space-time and creates correlations. These correlations appear as the particle detected by the two observers, or the squeezing effect that we have seen in our experiment. So these are two examples of physics cosmology in the laboratory. And if you would like to learn more about the background behind this, then I highly recommend these two books. So on quantum optics, from quantum measurements to black holes, and on the geometry and light, the science of invisibility, that explains some of the background of what I've said. Thank you very much for your attention.